Okay, it's 4:03, so I think we can begin. Hope everyone had a nice weekend. So welcome back, good afternoon to System Software. So today I want to begin by going over the homework. I think some of these questions, looking at them now, were just repeats of previous questions. So I guess number one, why doesn't a program have to open the standard in file? It inherits it from the parent process, which is going to be bash in many cases. Yeah, when you're running a program on the command line. What files comprise standard I/O? Oops. Yep, standard in, standard out, standard error. And what are their file descriptors? 0, 1, and 2. Exactly. Do you know which ones are which? Yeah, exactly. 0 is standard in, 1 is standard out, 2 is standard error. Number 3, write a bash command that uses ls-l and grep to find lines matching RW as a single pipeline. So this should be pretty easy, I think, right? ls-l, and what's the character that we use for the vertical bar, and then grep for RW. See that some files in this directory do have the RW permissions. So ls-l actually prints in a listing form, a long form, the permissions of each file. And by piping it to grep, we can grep for any files that have read-write in their permission list. Have a question? Or okay. Look like you were thinking for a second. All right. Number 4, write a snippet of code. I should fix this question to clarify that I would like to see C code that creates a pipe between two processes that redirects the first one standard out to the second one standard in. Use any programs you like. Yeah.
In the you went over this. I'm sorry, I don't remember fully. Why in the examples did you have us use a switch case instead of an if comparison for the 0?
You can use if you like, just that switch case is more idiomatic. I think you see that more often in examples in the man pages, and it makes sense. Also, there is a slight performance benefit to using switch case over if you can help it. Yeah.
Even over using Yoda style if?
What is Yoda style if?
Oh, I thought I was looking at this class when you put if 0 equals the thing instead of if the thing equals 0.
Oh, that. That's not going to change performance. That's more for robust programming and defensive programming. That's not really for improving performance. Yeah. Okay, so number 4, I guess should I show this? Should I give an example of this? Yeah. Okay. So I'll put this on the slide. What?
I would like to see it.
Yes. So let's do it. I'd like to see it. Okay. We'll create a file. Yeah.
I have a question about how you would expect on the exam. Would you expect us to write main and the whole thing, or just like it says a snippet of code of just basically the important part of it as well?
You should include main in your whole code. But honestly, it's not going to be much more, right?
Show that it's in main.
Yeah, show that it's in main. The program should be executable. Yeah. If you're asked a question like this in the exam, any code you write for the long response, let's say, should be executable. But it's not going to be much more to include main, right? You're just writing in main and then the curly braces and then closing curly braces. That's it. So, yeah. So that all being said, let's actually see an example of this. So we'll say vim, I'll call it, I don't know, pipeline.c. So we need our main function first. And here we'll set up the, what do we need? What are we going to need? What's some of this is called? What is something we're going to have to create? A pipe, right? So what's this called to be used to create a pipe? Pipe, exactly. So pipe, let me actually open the correct man pages. Here we go. It's in unistud.h. So I'll just copy that. And then we need a pipefd variable for storing, what is the store? Yes, the read and write end of the pipe, exactly. They're going to be placed in pipefd. So I'll paste this in here, the header we need, and I'll declare a variable pipefd of size 2. And what index is the index of the read end of the pipe? What's the value? What's the index of the read end of the pipe? 0. And then the write end is what? 1. So I'll define a macro here for the read and write ends of the pipe. I could use an enum instead. Yeah.
In the same vein, is there a question when we fill this out on a test and it should be executable, we want to include all of the libraries as well?
Don't worry about the headers. I'll put this in, this is going to be clearly, this is clearly spelled out in the exam. Don't worry about headers, don't worry about error checking for the exam. But you should always worry about error checking in practice. That's, people die because people don't check for errors in C code, so always check for errors. But for the exam, don't worry about it. It's a lot of extra code, but that's not really testing the core competencies of being able to use these system calls. So we'll say pipe, and then we'll pass our pipe FD here. Now, we've created the pipe, what else should we do? What should we do to, what? Yes, create processes. What system call do we use to do that? Fork, exactly. So we'll say switch fork. Oops. And I'll ignore error checking and just focus on case 0 and the default. Actually, I'll just put case -1 here just to be safe, I guess, just in case. Okay, we'll use exit, I guess. All right, so what is case 0? The parent or the child? The child, yes, exactly. So in the child, we're going to call one command. What command do we want to use? Well, let's actually, I'm asking you all as a question. What bash command do we want to make the child execute? Grep? Okay, sure. We'll call grep. So we'll use exec lp. So what does the L mean we can do?
Passes a list.
Pass them as a list directly to the command. Pass the arguments directly to the list. And then what does the p mean? You have access to the path variable, so we don't need to specify the full path to the binary that we're trying to run. So grep, and then we'll say null to terminate our argument list. And on the parent, we'll have to call another command. What should we call on the parent? What are we gonna, cat? Sure, that's a good one. That should be fine, yeah. We're gonna have to pass some input to grep since we're not passing a file name to it. We'll have to type something in manually at the command line, so we'll just take care of that when the time comes. Okay, so we have these two commands. We've forked the process here. It's split into two, and now we have to connect these commands to each other, connect the standard out to the pipe, the first command standard out to the pipe, and the second command standard into the pipe as well. So now, I guess, how should we do that? With dupe, exactly. So dupe2 is the one we probably want to use, not regular dupe. And we're trying to redirect the standard out of the first command to the right end of the pipe. So we're going to be using pipe fd, the right end of the pipe we said was at 1, so we'll say right. And we're also going to be using the file number for standard out, which should be standard out file name. So what order do these two arguments go in for the call to dupe2? This order? Okay. So we'll try this. I won't say whether or not it works. We'll try it first. After duplicating a file descriptor, if we no longer need it, what should we do? So which one are we closing here? Standard out or the right end of the pipe? Why are we not closing standard out?
Standard out gets closed by the dupe2.
It does get closed and reopened by dupe2 to point to the same underlying file description as the right end of the pipe. But that's not why we should close. Why we don't need to close standard out after calling dupe2.
That's the one pointing to the right end.
Yes.
The current
Yes. Yes. Exactly. So exec lp here, when it replaces the program with grep, will try to write to standard out. So we don't want to close standard out before it tries to write to standard out. Yeah.
Maybe a dumb question, but how likely is it you'll let us draw this on
Draw it?
Yeah.
Unless the question says draw it, you'll have to write the code.
Okay.
Yeah. But don't worry, because this is kind of formulaic. If you just learn this one example, you can kind of do everything else, because this is a really comprehensive example that has everything included in it. And if you don't want to do everything at once and you want to learn piece by piece, all the files are available online in the course website for you to learn each individual component and practice them. Okay, so we have this. I think we should exit with a -1 here, or the 1 in case of failure. Should exec_lp ever return? No, right? So we can just exit with -1, or 1 I should say, afterwards immediately, if it does continue. All right, now in the parent, what should we do? Do what? We'll just assume the parent is reading from the standard out of the child. We don't have to have the parent create 2 different children. We can just have the parent read from standard out of the child. Okay, so probably something like this, except we're going to change the arguments. So what should the first argument be? Okay, yeah, standard in file now. So that looks good. What should we close afterward? Yeah, the read end of the pipe, because we've already duplicated the file descriptor successfully. We don't need to, assuming we did it successfully, we no longer need that file descriptor because standard end is already referring to the right end of the pipe, or read end, I should say. Okay, now there's one more thing we have to do in the parent. Yes, wait, exactly. So we'll wait for the child to write, and then the parent will read. And we should also close one more file descriptor here in both the child and the parent. Before we even execute dupe, we should close another file descriptor in each of them.
You want to close a read in the child and the write in the parent?
Exactly. Why do we do that?
Because you're not using it.
Exactly. So the child's not going to be reading from the read end of the pipe. The child's reading from where?
Standard in.
Normal standard in, undirected. So we don't need to that descriptor at all in the child, so we should close it. Likewise, in the parent, we should probably close the right end of the pipe because the parent's writing to where? Standard out. So we don't need the right end of the pipe. So we can close it in the parent as well. So now we're going to have to include a bunch of includes here. So let's see. Fork is going to be in unistud. That's good. Exit's going to be in studlib. P error, I think, will be in printf. Or stdio, I should say. Stdio. Dupe2, unistud, close, unistud, underscore exit, exec_lp, I think, oh, sys/wait.h, okay, we got one more. Okay, now let's try making this, hopefully it works. This is pipeline.c, we have a syntax error near line 9. Int main void. I don't see a syntax error here. Oh, 2 arguments to wait. There we go. Okay, no error. This should be a.out because we didn't give a name to this file in GCC, so the default's going to be a.out. Let's try running it. We just get a message that grep needs an argument. So I guess since the standard in, since we've redirected standard in, or no, standard out, I'm not sure why, but for some reason grep here requires an argument. So we're going to have to pass a file to this. We can just pass, oh, we need to pass the pattern to grep, of course. That's what we need to pass. So what pattern do we want to search for? A. We'll just search for the letter A. Keep it simple. Let's try compiling again. and I'll just combine this with a double ampersand here, so the right-hand side gets executed only if the left-hand side succeeds, so I can quickly run these two commands at once. Okay, it seems like it's working. I can say hi, hello, awesome, and I'll press Control D to send the end of input signal to grep, and then we see awesome is printed back to us from cat. So maybe another example would be if we did this in a different way. Let's use different commands to show that this works.
I think it's the same example from question 3.
Yeah, we'll use the same example from question 3. All right, and here you can see we get the same output as for question 3. There's no colors, so a lot of these programs know when they're writing to a terminal or not, and they'll actually, inside the program, they can check this, and they'll actually disable their colorized output if they're not writing directly to a terminal output. So that's why you get no colors in this example here, but you do if I were to run the command ls-l, oops, wrong thing. Like this, you get colors. Okay, so questions on the last part here?
I remember
Yeah.
you mentioned about the wait for null, but I got confused. I just remember waiting for right was more important because that fancy word you use, where it's like a blockchain or something.
It's blocking. It's blocked.
Blocking.
The process is blocked. Yeah.
So what does the null do?
Null, so the syscall wait, if we look at the man pages, accepts one optional argument, because it says nullable, that's what that indicates, called wait status, this pointer argument. And in the description here, it should say this somewhere. Yeah. It suspends execution of the calling thread until one of its children terminates. The call wait status is equivalent to wait PID. And you can read more details of wait PID here, but the big idea is if we pass a non-null argument to wait status here, we can get information back about how the process terminated, how the child process terminated. If we pass null, we don't get that information back. We just wait until the process is done. We don't care about how it ended.
And how does it know it's done?
Through a signal. So remember, signals are another form of inter-process communication. So the parent receives a copy, I don't know exactly how this works, it's like an implementation, but the parent essentially receives a copy of the signal that was sent to the child to terminate it. And that's going to be given to you in the wait status argument if you passed it to the call to wait. Mm-hmm. Okay, so questions? All right. Okay, so today we can start talking about shells. So I think I mentioned this before, but all the projects and assignments we've been doing up to this point have been to equip you for this coming project PROC, which is assigned today, in which you'll be creating your own shell, basically. Your own miniature shell. You don't have to implement a lot of functionality, but you'll have to implement support for pipes, redirects, and forking and execing programs on your machine. So the first question, just to be clear, what exactly is a shell? Well, it's a command line interpreter. You pass commands to it in the command line, you're typing things in, and then they execute. And why is it called a shell? Well, I have this sort of comedic diagram here to explain it. I think I mentioned this before, but if we consider bash, the born-again shell, as sort of like a real shell, like a peanut shell, then what is the word for what is inside of a shell?
Kernel.
A kernel. So inside the shell is the kernel. Last semester when I gave this joke, some people were shaking their heads. I don't think everyone liked it. Put that back. Okay. So yeah, the actual English word for the inside of a peanut is kernel. So I don't know if that's really why it's called a kernel. I mean, it seems like just a joke to me. But. So to execute commands, as we've been seeing in this course, commands have a name, then we can give them arguments. But how does this actually work under the hood? So if I were to run the command given here, ls-l, we can see some output is given to us. But internally, Bash doesn't understand English text. So Bash isn't a person, it's a computer program. It can't understand what we mean by ls-l. And even if it could, that's not actually what's being given to Bash. In reality, what we're passing to Bash when we enter commands is just byte sequences. So to demonstrate this, I'm going to use the hexdump command, hexdump. Does anyone remember what this does? I think I showed it once in a previous lecture. Yeah?
It looks at the data in binary, but in hexadecimal, or the file you're trying to access.
Yes. So files are really what? What are files actually?
Memory.
Binary, like sequences of bytes, essentially. So with the hexdump command, we can get a view of the hexadecimal representation of the bytes underlying a file. So to demonstrate this, I have a file here called hello.sh. I'll use cat to print out its contents. You can see it just has the command echo hello in it. So I can run this file like hello.sh, and it'll echo out hello. But if I were to run hexdump on this file, hello.sh, you can see there's actually binary code inside this file, or really, it's just a sequences of bytes is all that this file really consists of. And if we actually pass the -c flag here, we can get a canonical view, which shows us on the right-hand side the ASCII decoding of this byte sequences inside the file. This is just to convey the fact that these files that we're passing to Bash and the commands we're passing to Bash are not actually text. They're really just byte sequences. So it's really just raw binary code that is what Bash actually reads. An abbreviation for hexdump-c is just HD. And just to be very clear, if you open the man pages for the ASCII table with man ASCII, you can actually scroll down here, and if I were to search for, let's see here, 65, that's where echo is. Right here, this is where it says lowercase e, and this is the hexadecimal column for the ASCII table, so we can see that lowercase e is indeed 65. So there's ways to do this for yourself and figure out what all these mean. Yeah.
What are the longer strings of zeros that lead into and out of this?
This is just a prefix of the line number, essentially, I believe. I don't think it's actually part of the file.
Oh, okay.
Yeah. And this last line is a new line character, 0A. So what I could do is to show this in another way. I could say echo hello. So I'm echoing that's the contents of that file here. I could pipe this to hexdump and then view it there. And there's actually a flag you can pass to echo to get rid of the new line character. And if I do that, there's no, well, the second line's here. Let's see, it's A, not B. And there's no extra new line character appended to the end of the output. So, yeah.
So it's not like a grid position in the document, it's just reserving where the cursor was left. It's at the end of the
Yeah,
first line.
I think so. I'm not really exactly sure what that left-hand side. I mean, you can probably read the man pages for hexdump and find out, but yeah. User specified format. I don't know what the default format is. You can probably read it and then it'll tell you, but yeah. The main event with hexdump is the hexadecimal representation. So, okay. Yeah. So in reality, what Bash has to do to be able to interpret these bytes we give it is perform this command loop here, where it first accepts some commands from the user, this user input, and then it performs a process known as parsing to convert that unstructured input, those raw sequences of text or binary values, into some structured form that Bash can actually interpret. And the term parsing will appear, you'll see it a lot in your computer science curriculum. It just means converting unstructured form text, textual input, or data into some structured form. So we'll be seeing parsing a lot in the second half of this course when we go to make our own compiler. And then after parsing the input, we get a series of commands. That's the structured form we get out of this unstructured input. And then we execute these commands with this like pseudocode here by running them. And we just keep doing this until the command given to us is exit. And of course you can see this is pseudocode. We haven't declared a command named exit anywhere, a single variable named command here anywhere, but presumably if the user overpasses something called exit, then we would just exit the loop. So this is the big idea. You just keep parsing and running commands until the user tells us to stop. And this is going to be how you implement your parser and interpreter for the shell project coming up. So this whole loop here is sometimes called a read, evaluate, print loop. You might have heard of this acronym before, a REPL. This is where it comes from. Okay. So the first step in processing these commands, converting this unstructured input to some structured form, is to identify the atomic, the elementary units of these sentences we're giving to bash, these commands we're giving to bash. And the word for these individual units, these like indivisible units, is tokens. So in this example here, the tokens of this command ls dot slash and then dot slash would be ls, oops, and then the dot slash and the dot slash. The command name and then its arguments are each individual tokens. This over here. Now for redirection, you might think, okay, well, this is easy, right? Like, all we have to do, like I know how I would do this, you just separate by white space. So some white space here, some white space here, and that's enough to determine where the tokens are. But with redirection, do we have white space between our tokens all the time, between the name of the file that we're redirecting to? Like, oops. I can write, for instance, ls-l out.txt, and that just works. There's no space between the greater than sign and out.txt, but this still, if I echo out the contents of out.txt now, you can see it still worked. So any mechanism we have for creating tokens needs to also support creating, determining what are the tokens in an input without necessarily relying on white space alone. Oops. For some reason, I'm having a hard time using my tool today. Oh my gosh. Did they change the hotkeys for this? Whatever, I'll just copy and paste everything. That works. Yeah. Yeah.
So to differentiate tokens, could you use like text them and then just see where like any sort of like operators or whatever are being used and then say like after that will be a new thing?
So you're getting to the idea of what's known as lexing or scanning or tokenizing, all different words for the same thing. And there's a lot of approaches to do this. What you're describing is kind of like a way of doing it, like the really vague terms, that there's a way to do it. And we'll be seeing, the good news is for the assignment, we're going to be giving you a lecture already. We're giving you a predefined, what's called a grammar, with the rules for creating tokens out of an input. And you'll be using that to already get the tokens of the input from the user for your shell. What you'll have to implement is the parsing part, converting those tokens into some structured form. But I'll be giving examples of this later in like the second half of this lecture. I'll be showing you how to get started with the project and tons of examples. But for now, the big idea, I just think it's appropriate in this class that you should at least be familiar with tokenization and how tokens are derived. When I took the course when I was an undergrad, we had to write the tokenizer, the lexer ourselves. So we had to create our own lexer as well. So, okay, any other questions about this? Okay. Yeah, so we need to also support, of course, other kinds of tokens. So ls/pipe wc. In this case, you would have a token for ls, a token for, see if I can do this. I don't know why, for some reason the normal commands I use to copy these boxes are not working.
Undo their last commit, get the version back.
Yeah, exactly. Okay, there we go. Yeah, so again, you need to be able to divide up the tokens. So we can already see that for our purposes, for our project, command names will have to be tokens, arguments will have to be tokens, redirection symbols will need to be tokens, and pipes will need to be tokens as well. Those are all different kinds of tokens. So how can we actually do this parsing? So kind of confusing parsing and lexing here, but we'll say parsing. So what are the symbols that we have for our inputs? Well, the ones we have are the redirection operators, redirect out, redirect in, the vertical bar for the pipe, and we'll just say string here in all caps to mean any contiguous sequence of letters or characters or numbers, and then \n for the end of a command. This isn't going to be an actual character we read, it's more so just going to signify the end of the input when the user presses enter on their keyboard. And then white space, well, they're not actually part of any symbol, they just delineate arguments. Now I will say there are languages, programming languages, which use white space as part of character names, or parts of names of like variables and whatnot. They're not languages that are meant to be used for any real application, they're just like kind of for fun to show that you could do it. But it makes parsing a lot more complex. So we're not going to include white space as any sort of token, it's just what separates the tokens, basically. Now to do this sort of parsing, can't really zoom in anymore, but I'll just go through this a little bit here. I'm going to go through this real quick. I know it looks kind of confusing, all this whole listing here, but then we're going to show how to use this in an example really quick. So the big idea is that we have in front of us a grammar, and grammar consists of these symbols on the left. These are called non-terminals because they result in some other set of symbols on the right. So this is called a production because it produces a set of symbols here on the right from some on the left. So in this case, our starting symbol for this grammar would be start, which then expands to a pipe, followed by a token, a \n character, the end of a line. Then from the pipes symbol, we have a command followed by any number of pipes. So the star here, this is called the clean star. It means 0 or more of the symbol that precedes it. So this means 0 or more of the pipe symbol, which is a pipe followed by a command, follows the first command in our input. One last thing I want to point out before I go into the example, these question marks mean 0 or 1. They mean an optional symbol. So this means that an out symbol is optional when you give a program, and the in symbol is optional when you are typing in a program's name. This is to make redirection in, redirection out optional, not mandatory. So I know this is again, confusing and boring, just seeing this listing. So I want to actually draw now a diagram showing how you'd actually use this grammar, follow the grammar to parse some input. So the input we're going to be parsing is the one here on the right. I'll make this a little bit smaller, this one a little bit bigger. Okay, so the first thing we're going to start with is what's the start symbol here on the left? What did I say the start symbol was? Start. So we'll start with the start symbol. It's a bit bigger. And yeah, blue is a good color. We'll use that. And the first thing we have to look for or structure for start is pipes. That's the first thing the start symbol produces in the production for the start symbol. Pipes. And then there will be a \n at the end. So we can put the \n here all the way on the right. Actually, \n is already provided for us. So we'll just connect a line to that now. And I think what I'll do is make this this line bendable. So I'll turn this to, where is it? Right here, and then make that, yeah. I'd rather use straight lines though, I don't know how to do that. We'll use curved lines. Okay, so we have the start symbol, expands to some pipes, and the start symbol, or in a \new line character. Underneath the pipes, we have a command and then any number of pipe. So underneath the pipe, we have a command, so I'll draw a command next. Command goes here. I'll make this a little bit shorter so we can have more space. And then any number of pipes. So we'll leave that for later. For now, we're just going to focus on parsing the command. So the command is followed by, let's see, command is right here, a program, and then an optional in, and then an optional out. So we'll first do the program. And a program is followed by, or it produces the production for a program is a string, and then any number of strings after that. So the string here would be cat. So we can say this program is coming from cat. So we can draw a line here, and then draw a line here, draw a line here. And then we can go back up to the next part of the command here in the left. There's an optional in for the command. So in is going to be a less than sign followed by a string. We have that here. There's a less than sign here, and then out.txt. So we'll say in. Draw a line connecting this, and then draw a line connecting this. And then an in is an optional, a less than sign, then a string. So we'll draw a line connecting this out.txt to the in. So we finished parsing at this point. There's no out, there's no redirect out character, so it's optional, so that's fine. We just don't parse that. And so now we go up. And we go back up to, where were we? Command we're done with. Pipe. Pipes here. So we had the command we finished parsing for pipes, and now it's 0 or more of the pipe star. So 0 or more of pipe. So a pipe consists of a pipe character and then a command. So we have a pipe character. So let's say there's a pipe here. And there's going to be a pipe that it consists of, followed by another command. So we can actually copy this here, and copy this here, and then connect these like so. And that's the parse tree for this input, cat reading in from out.txt, piping to WC, and then a new line character. So, question.
How come we didn't put like a pipe on the left, like underneath command?
Which under here?
Yeah, in between pipes and command.
In between pipes and command. Here, you mean like command and these two?
No, vertical, sorry.
Between these two?
Yeah.
So why didn't we put a pipe there? Because if we follow the grammar, we can see it's start, so start has to come first. Then it's followed by pipes, so we have pipes here. And then pipes starts with a command, so we go directly to a command. So there's no pipe underneath that one for the first command. Yeah.
Okay.
Mm-hmm.
Thank you.
You're welcome. Yeah.
Do you mind doing like that top to bottom flow again? Like,
Yeah.
flow path?
Yeah. So we started with a start symbol. A start symbol consists of pipes and then a new line character. That's what the \n here means. Maybe I can zoom in a bit more on this. Here's what I'll do. I'll copy this. And then I'll zoom in, so it's way easier to read. Hopefully that's better. Then I gotta maybe me see if I can get this working. Yeah, okay, that works. All right, so we started with start. It's right here. Then we went to pipes. It's going to be here. And then pipes is going to be a command. So we have our command here. And then for command, we have a program. So we go to program here. You're following so far?
Yeah.
And then for the program is going to be a string followed by any other number of strings. Well, we only have one string, oops, cat. We said that a redirect in is not a string, it's its own special terminal, its own special token. So we finished parsing command, or program I should say. So we can go back up to command. So after program, we have an optional in, and in is going to be a less than sign followed by a string.
Why did it go back to command?
We finished parsing command. So there was we finished parsing the program. So a program is a string followed by any number of strings. We parsed the one string and there were no more strings after that. So we finished parsing program. So then we go back up to command because that's what it told us to start parsing a program as part of that rule. Then move on to the input, or in I should say. So in is going to be a less than sign followed by a string. So we have in here, we have the less than sign, and we have the out.txt. So that finishes parsing in. Then we can check if we can parse out. It's optional, so if we don't have the necessary inputs to parse it, that's fine. Out requires a greater than sign followed by a string, but the next symbol here is a pipe. It's not a greater than sign. So there is no out. So we finished parsing the input, the command now. We finished parsing all of command. So we go back up to what we were doing to parse command, and we were parsing pipes as part of command. So now we go back up to pipes. Pipes. And now we see the next element of pipes is pipe star, so 0 or more pipes. So a pipe begins with a vertical bar. We see there's a vertical bar here, so we should expect to find a command afterward. That's the next thing in a command, or in a pipe, a command. So then for this command, we would follow the same steps. We would parse the program, parse the string that program has. There's no input or output, no redirection in, no redirection out, I should say. And so we go back up. There's nothing else left to parse for program, nothing else left to parse for command. We finish parsing pipe, and then we're back to pipe star here. But there's not another vertical bar, so there's no more pipes. So we go back up to pipes top, the pipe symbol, and then parse the last character, the new line character. And that's it. Yep. Yeah.
Use like C code to like implement this?
So you'll be given C code that creates the tokens for you. And what you will have to do is form not this parse tree structure, but we'll be giving you a command struct that you just fill in with these inputs. But in the second half of the course, these parse trees will reappear, and you'll be navigating these trees to write a compiler to translate high-level code to assembly code. So we'll be seeing this concept again. I just want to introduce it to you now because we're talking about parsing and lexing. It's very relevant. Yeah. This is something that every computer scientist, every programmer should really know, be at least somewhat familiar with. This is called an abstract syntax tree, when you break the elements of syntax of an input down into this tree-like structure. Okay, so let's go back to the slides. And I think this might be a good point to stop and take attendance. So let me fix my notes here. They're all kind of moved around. Okay, that should be good. I'll pause the recording here and then I'll take attendance. Okay, so it's 4:55. I think we can resume from here and keep going. So, big idea of how we use this grammar, I just walk through this. You just follow each symbol and then follow the productions that it has, the symbols on the right-hand side, recursively until you create a tree or parse the entire grammar. So that's the illustration we had here as a result of doing that. Let me actually stop the UCF here session. I'll fix that later, but I should be able to fix this later. Okay. Yeah, then we saw this as well, parsing strings. Now the way this actually works in practice, the way this would actually look like if we were to walk through this step by step with this pseudocode here is let's imagine there's some sort of marker we have telling us what the, oops, that's not right, there we go, the current token is. The pseudocode for how the actual parsing works is that we start with the token and then we try to match the start symbol, the pipes, the command, a program. We consume one or more strings. Consume means to advance the token forward, expecting that as an input. So we consume the string here, cat, which is a string. Then we check, is there an in? If the next token is the less than sign, then consume it and then consume a string. So we expect a string to be next after the redirect in symbol. So we have this out.txt here, so we consume that as well. Then we match an out. There is no out, so we do nothing, optionally, yeah. And then we match any number of pipes. If the next character is a vertical bar, consume it and repeat matching a command. So we consume the vertical bar, and now we go back to matching a command. So we match a program, one or more strings. We don't match any redirect in, we don't match any redirect out, we don't match any more pipes, but we match the new line character here at the end, and then we finish with the loop, and the whole command sequence has been parsed. Yeah.
I don't know if this is like not understanding it, but you like didn't go through the block packaging.
So this is like how the implementation would actually look. This isn't the whole tree structure. This is conceptually what we're doing is creating this tree structure. But what the code would actually do to walk through this would be to essentially this is just to parse. It's not necessarily to actually really recognize the input to make sure that it conforms to the grammar. This isn't actually creating any structure from it. So this is the kind of code you would write, something like this, to just check that the input conforms to some grammar, where you match the symbols one at a time. This is actually called a top-down parser, this approach. But really we're making a recognizer where we just confirm that the input is valid, not necessarily converting it to any structured form. So that's why we skipped the whole tree thing this time. Yeah.
Thank you.
Okay, so let's go on. So how do we actually implement this? Well, like I said, we're giving you a lexer already. We're using a tool called Flex. So the field of parsing and compilation is one of the most well-studied fields in computer science, and there's a ton of tools out there, but some of which we'll be using in this course, that let you specify a grammar, so a input that looks sort of like this, and give it to one of these programs, and they'll generate for you a program that can parse input that you give it. And then the parser can be implemented automatically in C, Python, etc., Java. So you don't have to worry about actually writing a parser, you just write a grammar and then a parser is generated for you. So we're going to be using one of these parser generators for this assignment. We're using one called Flex. And it gives you these lex.l files, or lex.c files I should say, as output. It takes a lex.l file as input, specifying a grammar. And then it generates the parser for you in a lex.c file. So I'll be showing you this shortly and in the example. This is all to say, you do not have to write the lexer yourself. We're giving you the lexer. Now there's these different kinds of tokens that you'll be using. These are the same tokens we've seen on the right here so far. So string tokens, pipe tokens, redirect in, redirect out, and then the end of line. These are the, I think it's 5 different kinds of tokens we'll be using for this assignment. And then in the parser itself, there's going to be some functions, some global variables we'll be using to store information about what's been parsed. So the look ahead will store the next token that we have just parsed in the input. and then the lexeme variable will store the text of the token we just parsed. And the function consume is what we can use to read the next token from the lexer. So in this example, what are the tokens and what are the lexemes? So what is the type of this token ls? Yeah, it's a string. The type of this token. Yeah, redirect in. What would this be? A string. Here, the vertical bar, pipe, and then a string. And the lexemes are just the text of each token itself. So the lexeme for ls, for the token, the string token ls is just the text ls. So, yeah. Okay, let's see if, all right. So last thing before we get into the example, yeah, we're using this global function consume to advance the parser by one token. And we have these two functions available to us, ensure and match. And ensure, make sure that a token is what we expect it to be. This is to prevent our user from passing input like ls pipe bar out.txt. Well, I guess that works. What's some input that I guess is invalid? Ls yeah. So I think that actually works. My ligatures that I have make it look like a funny character, but basically this is an invalid syntax here, invalid input. It doesn't follow the syntax. You have a redirect in, there's no string following it, instead we just have a pipe character. So this should be something that throws an error. So we'll be using this function here, ensure, you'll be using it in your assignment to protect against such cases where the input is just totally invalid. And for cases where some part of the input is optional, like how we saw back here, the redirect in, redirect out of a program is optional. You'll be using the match function instead for doing that. And if a match is not found, it just returns false. It doesn't actually crash your program. So now I think that's enough talking. Let's finally get into the examples, what I've been looking forward to. I'll minimize this, or I'll put this over here actually. Close that. Okay, good. I'm recording. This on the right. And for your project, you're going to be given this proc.tar file. You'll have to download it. It will have all the starter code for your assignment. So I'm going to go into this directory now. I've already extracted it. So I'll go into the proc directory. And what you'll have to start off with are these files here. So what you're supposed to do, and there'll be instructions on how to do this, you'll want to rename the mysh.template.c file to just mysh.c. And from within here, now we can start writing our program. So we'll open mysh.c, and I'm going to walk through this file line by line just to show you how to get started with working on this project, because it is a bit more comprehensive than the previous projects. So the first thing you'll see here are all these includes. They're just for all the syscalls here listed on the right, different functions. There's this tokens.h file. If we go to here, you can see the tokens listed in this file are the exact same tokens as we saw over here. They're just the corresponding C code for these different kinds of tokens. So we'll be using this to detect what kinds of tokens the user has passed to you. There's a util.h file that we give you. I recommend looking at the header file, and it will show you all the different functions you're allowed to call that we give to you. You're allowed to call more than these, but we give you these functions for helping you with writing your shell. So one thing of note here is this command struct. We'll see more of this later, but we define a struct for you to use to create commands, parse commands, and give them structure. So I'll explain more of these as we use them throughout this rest of this lecture. If you're curious about how all these functions are implemented, you can look at the util.c file, and this has implementations of all the functions that are in util.h. So if you just want to see how something works under the hood, you can check it out if you want to. So now there's this lex.c file, and you'll notice that if I try to jump to the file here with gf and vim, it'll say can't find file lex.c in path. That's because this file is generated from lex.l. So the tool we're using that we mentioned, Flex, is going to be generating this lex.c file for you. The lex.l file contains the grammar specification for Flex. So this is kind of weird to look at. You don't really need to know how this works. The big idea is that this is the specification, the lex specification of the grammar here on the left. And Flex can read this and generate a C program capable of parsing this input here on the left. So if you're curious, you can read up more about Flex and see how this works. For our purposes, you don't really need to know exactly how this actually works. You just need to know what it does. So the first global variable you have access to is this look-ahead variable. It stores the next token to be parsed. And the lexeme variable stores the text of the look-ahead, so the underlying text of it. This consume function takes one token from the lexer, and this parse command is what you're going to be implementing yourself, one of the two commands you'll be implementing. And then the run commands function as well, you'll be implementing that also to actually execute the commands after they've been parsed. So if you're curious, this is how the consume function works. We're calling this yylex function, which is given to us by the program Flex for parsing the next token in the input. And then we use this copy string function that is defined in util.c to just copy the text of that string to the lexeme global variables. This is how these global variables are populated. And in main, we're just calling parse and then run commands. So now it's up to you in your project to actually implement the parser and then the functionality for running those commands. So to show you how you can get started with this, let's take some partial implementation here. This doesn't actually do any parsing. This just does what's called recognizing. So it, again, reads the input and makes sure that it conforms to the grammar specifications, but it doesn't actually convert that input to a structured form. So you'll see in this input here, we have the way this project works, or the way this template code that we're giving you works, is that we have some commands here, or a command. We have some labels, I should say, denoting what part of the grammar we're parsing. So the first part of the grammar that we're going to parse is a command. And the first thing to do that is to ensure that the look-ahead symbol is a string. The look-ahead token is a string. So again, if we go back to the grammar, right here, the first thing we do, well, pipes goes to command. So the first actual thing with like the first actual part of input that actually has something to parse would be a command. So program and then string. So we start with command and then program, and then yeah, from here we have to actually ensure there's a string that follows. So to show how this would work on like an example of actual code, again, if we have this input here, ls, we would first the input would be, the token would be somewhere over here, the current token. So we call consume to sort of like prime the pump and get the tokenizer ready. Place this here. Then in the command label here, we ensure that the next token is a string, which we can verify it is. ls is a string. Then we move on to program. So actually, I guess before I continue, are we all familiar with how labels work in C? So labels, they don't really do anything themselves. You can write labels in your code and it doesn't affect the functionality of your code. They just let you use the goto command to jump to a label. So goto command is generally considered something bad to use, like it's bad practice to use goto a lot, but there are some uses for it, and I won't spoil it, but there's a very nice usage for it in this project. If you want to use goto, there's a very slick way to implement this function using goto. So you can maybe figure that out as you write the project. Okay, so anyway, then we ensure the next token is a string. It is. We go to program, ensure that it's a string. It is. So we consume that token. Now, what we have to do next this is only partially implemented, but we would check for an input, we wouldn't find any. We check for an output redirect. We match, so remember match returns false if it's no match is found, true if a match is found. We try to match a redirect out token. We find that there is one here, so we consume it, and then go over to the next token. We ensure this is a string, it is, so we consume that token, and then go to the new line character, and at the very end, we ensure that there is an end of line at the end of this input, and that would succeed. So that's just kind of how the code would actually work here, going through some simple input. Yeah, okay. So any questions so far? Yeah.
Okay, sorry. So what we'd be doing is essentially like just fully writing out like the pseudocode that you showed earlier and stuff.
Yeah, you'll be completing these to-dos here, essentially. Just look at the to-dos, let them guide you. And you can test I'll show you how to test your code as well. But to give you an example of how this would look, just like a really easy example, low-hanging fruit, I can copy, so VIP, view in paragraph, and vim. I can yank this with Y. I'll copy all the code for implementing, checking for the out redirect. I'll paste it right here, change this to in, and now we can add support for in redirects with changing this to redirect in. And now we're able to support parsing input, or redirect in, I should say. So what does this actually look like? Well, let me run make. So we compiled our project. And now I'll try and run my shell. And now if we run a command like ls, we get no output. The reason why is because it's just verifying that the input was correct. We're not actually printing anything yet. So I can say my shell ls, and then what I could do to make sure it works is echo out the exit code of the last command, so that my shell program will exit out its exit code, and it's 0 meaning success. So it seems like the parser was able to recognize that input. Now if I type in something invalid, like ls, and then something we haven't added support for yet, like pipes, we get a parsing error message. So if you do something wrong, you're going to get a parsing error message, and if you check the exit code as well, it would be 1. So let's check again with what we've added so far. We should be able to support something like this, where we pat out.txt, and then redirect it to out2.txt, and that seems to work. So far what we've implemented seems to be working. And you don't have to worry about the case where the user specifies the redirect in after redirect out. For our purposes, you can assume the user is going to always provide the redirect in before the redirect out, if they provide one. Okay, so any more questions on this so far? Hopefully this is giving you an idea of how you're going to tackle this project. Yeah. Okay, so what we have to actually do, though, to run commands is first give these commands that we're reading in some sort of structure, some kind of memory layout that C understands. And to do that, we're going to be using this program here, or this struct here on the left, command T. So this is going to be defined in util.h, right here. It has this list of arguments, max args, which is defined up here to be just 64. So you can just assume the user's not going to give you more than 64 arguments. And the end should be null. It says in the comments that this is a null terminated list, so make sure to always assign the end of this list to null. Actually, you don't have to do that because, I'll explain why in a second, but you don't have to worry about that. You shouldn't have to worry about assigning it to null. There's an in field here for each command, which is going to be the name of what we're redirecting in from, the name of the file we're redirecting in from. If it's null, you can assume there wasn't a redirect. If it's out, that means there is the same thing for out. If out is null, there's no redirect out. And then we have a pointer here to the next command. What is this? What data structure does this represent then, since we have a pointer to the next element?
Linked list.
A linked list, exactly. So these commands are implemented as a linked list. So if we're working with these commands, we give you two global variables, first command and last command. You can use these to quickly get the first and last command in the linked list of commands that you're creating. So to create a command, you can use this add command function to quickly create a new command and append it to the end of the linked list. And the reason why you don't have to worry about assigning anything to null inside here explicitly is because this add command function is going to use calloc, I believe, under the hood. So if I were to go to the source code here for util.c and then add command, actually it doesn't even use calloc, it just manually assigns everything to null. So we don't have to worry about assigning fields that we don't use to null ourselves, they're just already going to be assigned to null by default. Let's see if there's an example here that I can throw in. Yeah. And we'll just call print commands here to pretty print all the commands that were given to us. So what I want us to do is to be able to call print commands here and print all the commands that are in the list. But first thing we need to do up here now is actually start creating some commands. I'm going to copy what we have here. Let me make sure I get it all. Yeah. Okay, so now the difference that we have, we made some changes. We've added this command variable here by calling add command to create a new command, a new pointer to a command. And then down here, next we parse the program. We assign the first field of the argv, first element of the argv field of the command to the lexeme. So when we call a program, what is implicitly passed as the first argument? The name of the program itself, right? So that's why we store the name of the program here as the first element of this argv. And then when matching a redirect out, we can actually assign the lexeme of whatever we just parsed. So at this point, again, if we go back to the example, we're trying to match an out. We're in the out label, I should say. We match the redirect out token. So we consume that token. We ensure that the next token is a string. Then we assign the out field of this command to the lexeme of this token here, out.txt, and then consume that token. So then we go on to the new line character. So now down here, we're calling print commands. I don't think we call free commands anywhere. So there is another command that another function we should probably be aware of, called free commands. Where is it? Well, it's not given, but I'm gonna call it anyway because we should probably be doing that. Oh, wait, oops. This will just walk the linked list and free all the elements in it. Okay, so now let's try running this. Make my shell, and let's type in a command like ls, and we can see it actually prints the command back to us. Now if I type in my shell ls or cat and then redirect in from out.txt, we get a parsing. Oh yeah, why did I get a parsing error? So it's because I'm trying to redirect in, but have we implemented redirect in yet? Yeah, I deleted it when I threw in this new code for parsing commands. So we don't have support for redirecting in. So I'll actually show you how to add that shortly as well. So let's run this again, and now we'll say ls to out.txt, and we actually get it pretty printed back to us where there's a space between each individual token. So you can use this to sort of just check that your parser is working. I don't think the test cases will actually be checking any pretty printing. We're actually going to be checking that your shell works, not that it pretty prints things. So to implement the redirecting in functionality, it's as simple again as just changing out to in. And instead of changing command assigning command out to the lexeme, we'll assign command into the lexeme. And now if we run make, oh, oops, gotta change the label as well. Now if we run make, and then run the shell, type in, we can now do out.txt, out.txt, and it actually works, and we're able to parse the whole input. So to accelerate your testing when you're working on this project, I recommend actually just using something like echo to echo some commands directly to my shell at .sh. Because you don't want to have to run the shell and then press enter and type in a command and press enter. That's really annoying. It's faster if we could, like, you know, just press Control P or up arrow and then enter, just keep running tests, or there's even a faster way than that. But it'd be nicer if we could just run our test with one command. So the way to do that is to just echo a command you want to run to your, and pipe it to your shell project. And with that, you can actually get the same effect. Since your shell is just reading from standard in anyway, you can actually echo, yeah, some text to your shell, and it will just execute whatever you echo to it. So if you really want to get crazy with this, not crazy, but maybe do this smart, like work smart, not hard, as they say, you can create a new command here in your make file. Make sure it's the last command you add, the last rule you add, because we're going to assume the first rule is to compile your project, so make sure to add this as not the first rule. You can call it test, and then you can actually put in here a series of tests you want to do for your project. So we could say echo, again, just this. You can copy this whole thing in. Oops. Yeah. And now if I run make test, it will actually run that test for me immediately. So I don't have to worry about it not working. We're going to give you test cases too. So what you could do is actually just write your tests and make to your test recipe and make to just run the tests that we give you. So you can quickly test your program. And just to show you another way to speed up your development workflow here, I think I've shown this before, but just to remind you all, Vim has built-in support for make. So I can call make from within Vim, and it will actually try and compile my code. And I can even pass, if I want to, specific commands to make from within Vim. And then it will actually run the test cases for me. So you don't have to leave Vim. You can just, or whatever editor you want to use. I'm sure there's something in Emacs to do this as well. You can just work on your program, add functionality, and then run make, and then it works. Or make tests, I should say. So a good way to like develop for this would be you could have multiple tests because make will crash when a command that it tries to run doesn't work. You could have multiple tests for different inputs. So I could say one test for just a string by itself, for a command by itself, one test for a command with only a redirect out, one test for a redirect in, and then one test for redirect in and redirect out. So we could say here out.txt and then out.txt, out2.txt. And now let's pretend I commented this out. I could run make test, see that a single test here. Oh, wait a second, this should fail. Oh, I didn't make the main a dependency here. So we recompile, make test. Yeah, and we had a parsing error. Then if I were working on this and I implemented this functionality, I could run the tests again, and then it would actually all now work. So just an example of how you could quickly like make your development workflow a lot faster. But if you do this, make sure to make the program a dependency of tests so that whenever you try to run your tests, make will recompile your code if it needs to be recompiled before it runs the tests. Just make sure to do that. So you don't have to do any of this. You can just run all these tests manually from the command line if you want to, but that's going to be a lot slower and more painful. So you'll save more time if you spend like, I don't know, 5 minutes up front learning how to do this. Then you can save yourself a lot of pain of manually testing all your commands in the future. So You could also just write a bash script that has all the different commands you want to run in it, but I think this is a better way. Okay, any questions? Okay, so with the parser we have, what we should be getting from this parse function is this command list. We should have parsed all the commands and converted them to this list of commands. Now what we can do is interpret these commands to actually execute them. So an interpreter is something that reads source code and then executes it, as opposed to a compiler which reads code and then translates it to a machine-readable format. An interpreter just reads code and then executes it immediately. So for us, we're going to be writing this run commands function here is going to be our interpreter, or what's going to be interpreting our commands. So to give an example, I guess the source code, you only have to add support for one pipe. So you can just have in your implementation of the run commands function, one command, a way in which to handle one command, and then a different behavior for handling two commands, and that's it. And this, you can just read this source code, this pseudocode. It's online if you want to refer to it. It'll be in the course notes. In previous semesters, we actually had students implement support for two pipes, but honestly, that was almost harder than implementing supports for any number of pipes, because to implement two pipes, you need a bunch of different if conditions, and it's really annoying. At that point, you're better off just implementing like an arbitrary number of pipes. So now we only have students do one pipe, because it's honestly a lot easier than trying to implement two. Okay, so yeah, I mean, what's this called? Do we use to execute programs?
Fork exec.
Fork and exec, right? So that's what we're going to be using in the implementation here now. So it's all going to finally come together, hopefully. And then you can imagine how all these redirects that we've been using, these redirects, what's this called we're going to use to implement these? Dupe, right? So we actually have everything we need to start implementing, our own shell. And you'll see that now. So I'm going to copy this code here for the running commands. It's a lot of code. Let's see if I can get it all. All right, I think I'm going to close the notes now. I think we're done with those. Now we're just going to focus on the commands here. So the big idea with what the code, and all this code again, all this starter code is given to you online. When you download the proc tarball, the tar file, it's not going to have this in it, but you can just go to the course notes underneath the shells section, and you'll be able to see that all this starter code is there for you to start with. So I recommend just doing that to quickly skip past a lot of like boilerplate annoying work and just get straight to the actual hard part of the assignment. So in this run commands function, the first thing you do is check if the first command is not null and the last command is equal to the first command. That means we only have one command. So in this case, we only have to support executing one. We only have to fork once, create one child. So in the child, we do our normal trick here of switch fork, and we actually get the child's PID. I'm not sure if we actually use it anywhere, but we get it. We handle an error, and then within the child process, we check if command out is not equal to null. That means that there was a redirect out, so we open the file for redirecting out, and checking that it succeeds. Then if it did, we can redirect the standard out of the child to that out file. And we no longer need to have it open. We can close it because we've redirected standard out successfully, so we can assume that we no longer need the file descriptor that we initially got from open. And then we can call exec_vp, and the way this call is working is the first arguments. Remember, we had said the first argument to exec is always going to be the name of the program, and the first element of that argv field that we populated in the command struct was also the name of the program. So you can actually just use argv0 here when calling exec_vp. One thing you'll have to do is get the rest of the arguments. So I think one of the to-dos here is, yeah, collect the arguments as well, so we don't have support for that. So right now we can only execute commands that don't accept arguments because of that. Then in the parent, we just wait for the child to finish running. That's it. And notice that we actually only support running one command right now. So you'll have to add support for yourself, possibly with like an else if statement here, for running multiple commands that are connected by a pipe. So now why don't we try running this? So I'll say make, and let's run the my shell. And if I type in ls, you can see it actually works. And we added support for a redirect out here. So let's try running that as well. My shell ls out.txt. We got no output. That's a good sign. And if we cat out the contents of out.txt, it has all the contents of our current directory. So it seems like it's working. So how can we add support for redirecting in?
You guys can write it.
How would we write it? What would we have to write? Like, you can just describe it in general terms. What would we use to redirect in?
We'll check if it's null first.
Okay, so I'll grab this, paste it down here. If null is not equal to command in, then what do we have to do first?
It's file descriptor.
Get the file descriptor, right? So we'll say int infd is equal to open, and so we can get it from the in field of the command, which should be populated for us if we parse the input correctly. And then what mode should we open the file for? File with? Read only, right? Because we're only reading. We're not trying to write to it. We're just redirecting standard in.
What's the other one not right only?
I don't know why. Dr. Gazilla wrote this code. I don't know why he gave it a read write. You could just, I don't think we're going to be writing to it, so you could just replace this whole thing with, what command did we see? Yeah, create, like that, if you wanted to. And it should be fine. I don't see why you need to open this for read write. Okay, so now we're opening this command for read only. We can check for an error. What should the value be if it's an error? Yeah. I'm just going to write it pretty concisely like this. I don't want to take up a bunch of space. Okay, and then after opening the file, how can we redirect standard in? Duke2. And then what's the first argument? NFD. And then standard in file node. Okay, then we can put this all in a if statement as well.
Would you close the read side first? I mean, right side?
What do you mean? Oh, what do you mean?
Like when we do before, if it was the read end, then we would close the right of it, and if it was the right.
Oh, are we dealing with pipes? Have we made any pipes yet?
No.
Yeah, right now we're just doing redirection, not pipes.
You already forked though, so wouldn't you want to use underscore exit?
We should. Yeah, we should. I think, so when Dr. Gazilla teaches this course, he doesn't like using underscore exit. He prefers to just do exit because he doesn't want to explain underscore exit, but I think it's fine to explain it. So I prefer to use it. So these examples came from him, so that's why you don't see them here. But you could add underscore exit to all of these if you wanted to. Yeah. Okay, so we've successfully duplicated. Now, the last thing we want to do, what do we want to do with the file descriptor after we've redirected it?
Close it.
Close it. So I'll just copy this here. And a lot of this stuff you can just copy and paste when you're doing the assignment yourself. Okay, and I think that's it. So now we should have redirection support for in redirection. So now if we were to run our program again, oops, Oh, I forgot to change create back to open. There we go. Now I can say cat out.txt, and what do you know, it seems like it's working. So I don't know, I think it's kind of cool. We were able to write our own shell, and it actually just works. So now that you see how a shell actually works under the hood, how do you think we could add built-ins, shell built-ins like CD and whatnot? How do you think they're implemented?
Could you make like one of those like indentation thingies, and then just like add all of the you would add all of the like
Code?
the
Or-
well no not code well yes code but like the consume and then rid of the mix.
So that's for parsing them, but how do we think the functionality of a built-in like CD is implemented? Do we think a call to exec is made?
Yes.
Yeah.
No, right? I mean, well, it's built in. That's why it's called a built-in. So if we want to implement a function like CD, what we would do is have a global variable up here saying, or maybe like a char star saying current working directory, and then what our CD function would do is just assign CWD to whatever the destination is. And this isn't exactly how Bash does it, but the idea is that some of the functions in Bash, the built-in ones that we've been seeing, are just functions in C implemented directly in Bash. That's why they're called built-ins. They're built in directly into Bash. And CD has to be a built-in because it's changing an internal variable storing the current working directory. So it's not going to look exactly like this, the actual Bash implementation, but this is probably conceptually the same thing that's going on. So in earlier versions of this course, we actually asked you as part of the assignment to also implement some built-ins like echo as well. We don't have to do that for this assignment. You can just use exec, fork exec for everything. Yeah.
So it's the same as like it just clocked me. It's the same as the like run command like thing.
Like it's a function we defined ourselves.
Oh.
Except the only difference is when you're going in to run commands, you'd have a check like is the name of the program CD, and if it is, then you just call the built-in function CD instead of calling fork exec. Yeah. But to keep things simpler for you all, we just assume you can fork exec everything. Yeah. Okay, so any questions? Okay, so I'm going to close this window then. And just want to review something here. The MyFine project is due in our next lecture. The proc project is assigned tonight, so start working on it early. It's going to be due in, 3 weeks. That should be plenty of time. Yeah.
Five is due by like homework style by the start of our next lecture or by midnight that night?
It's due at 11:59 p.m. The course notes say this, I believe, right? Yeah. Exercises and projects are due at 11:59 p.m. I might change homework to be due at a different time in the future because people don't like it being due at an unusual time. But, oh well. Okay, but yeah, so if you have any questions on these projects, please come and ask me. I have office hours. You can come to me afterwards as well. Otherwise, I'll see you next time for midterm review. We'll be preparing for that.
So it says midterm.
What?
You're passing over a typo right now.
Oh, oops. I'll fix that. Thanks.